Hello, this is Professor Stephen Neshiba, and I'm here to help you out with the Computational Guided Inquiry for PChem. This one is about visualizing U of T, the internal energy as a function of volume and temperature. So here's the handout for this, and here's our objectives. We want to help you build some intuition about thermodynamic surfaces. Here's some self-assessments that you'll want to have a look at. And there's a kind of a longish introduction. There's some equations here. For example, is the internal energy of an ideal monatomic gas, and so on. Much of what we'll be talking about in this exercise is curves like this. This is the internal energy of a gas as a function of temperature. And you can see that it forms almost a straight line, but it's not quite a straight line, and it turns out that sort of thing is important. We'll also be talking about the intermolecular potential energy between a couple of gas molecules and the fact that it's got regions of attraction and regions of repulsion between the gases. But let me go ahead and skip right down to the pre-lab part. So if you're watching this already, then you've already taken on the first step of the preparation. Second step is to use equations 1, 4, and 5 of this handout to predict the constant volume heat capacity, CV, and the internal pressure of an ideal monatomic gas, and record those values in your notebook. That will take you'll have to study those equations and do a little calculus. Next, you'll need to download some thermodynamic surfaces, etc. And let me just take you back to the Moodle page to show you where they are. So here's the video that you're watching right now. There is, by the way, another useful video from UC Berkeley that has to do with condensation and intermolecular attractions. But here are all the text files that you want to download, and you may as well, if you like, you can download these template Python files. All right, so once you've done that, then you'll look at the shape of each one of those, and you'll be good to go. So now, during class, this is what you're going to be doing. You'll be looking at each of the following steps for each thermodynamic surface. Each thermodynamic surface that you downloaded, that's ugrid1.txt, and so forth. Now, here's the mystery of this exercise. One of those represents an ideal monatomic gas, another represents an ideal molecular gas, a gas made up of molecules, and another one is a real gas, and your task will be to find out which one is which. So the first thing to do here is you're going to graph the 5-liter isochore of each one of those thermodynamic surfaces as a function of temperature. Now, what do we mean by an isochore? Let me take you back up to this picture here. So here is a thermodynamic surface. Its internal energy is a function of volume there and temperature there. And what's an isochore? Well, that's a line of constant volume, and we would be looking along here. An isochore then would be U as it increases as we increase the temperature but hold the volume constant. And so that's that first part of that. So that's going to be just a simple one-dimensional graph. Now let's go back to Python here, and I've already got this template up and going. I've already oh no, I haven't. I'll have to set the working directory. Remember, this has got to get set to the PChem folder. And let's see, there's my PChem script folder. That's good. And so then I get to go back to Python, and well, now actually this one is looking pretty good to me. Loads, we need to load in the volumes as the set of axes and the temperatures. That's good. ugrid1.txt, that's the first one of those thermodynamic surfaces. Here we've already set this up. It's row 23, which corresponds to a volume of 5 liters. That's because these thermodynamic surfaces, they're organized in terms of rows and columns, and the rows tell you which volume we're at, and the columns tell you which temperature we're at. So saying row 23 sort of fixes us to be at a volume of 5 liters. So that's what makes this an isochore. And the rest of this looks okay. I think maybe I can just try to run this and we can see what happens. Oh, and there we go. Here it's temperature on this axis, internal energy on that axis, and you can see that it's not a straight line, and that turns out to be important. Okay, so let's go on to the next step here. Graph the 300K isotherm. That means what you're going to be doing is looking at different volumes but holding the temperature constant. And it turns out the 300K isotherm corresponds to column number 49 in that grid file. So let's go back to Canopy, and I think I can find this one here. This is the template if you wanted to try to use that. Oh, well, it's not going to help very much because I've had you do all this. But once you do that, then you'll be able to make a similar graph to what we just looked at for the isochores. Now, what's the third step here? The third step is to display the 3 supplied internal energy files, the grid files, as thermodynamic surfaces. Those are, two-dimensional plots, and we can look at that script file UVT3 for a little bit of help on that. So there's the template that you could have downloaded. This stuff at the top, that's pretty much boilerplate. We load in the volume, we load in the temperature, we load in the U-grid, and so forth. We have to lay out the temperatures and the volumes as a mesh in the same way that the U-grid is, and that's turns out this is the proper order to do that in. I've left out plotting the surface there because you can probably figure that out, I hope, on your own. But if you don't remember what to do, you can go back to pd1.py and that loaded in all the grid stuff, and then you would need to copy over this graphic stuff and make appropriate changes, and then you'll be able to get that done.